Dear students, in the chapter of forced vibration, in this lecture we will be discussing the problems on equation of motion of a vibration system, forced vibration system, subjected to harmonic force. I, Dr. Balraj Singh Brad from Yadavindra College of Engineering, Talwandi Sabo, India, am presenting the lecture. The problem is a mass of 200 kg Mass of 200 kg is suspended on a spring having a stiffness of 20 kilonewton per meter and is acted upon by a harmonic force 50 Newton magnitude. So the force is having a magnitude of 50 Newton and is harmonic, so can be represented by sine or cosine curve at the undamped natural frequency. So what it means is the harmonic force frequency is equal to the natural frequency of the system, undamped natural frequency of the system. So given is frequency ratio omega by omega n is 1 means the system is vibrating at resonance. This is given in the problem. The damping may be considered to be viscous. It is a viscous damping problem and a damping coefficient is 200 Newton second per meter. So C damping coefficient is given 200 Newton second per meter. So in this spring mass damper system subjected to a forced vibration harmonic force, the different terms have been given. Now we have to calculate the undamped natural frequency, means we have to calculate omega n, the amplitude of vibration of the mass A, the phase difference between the force and the displacement, means we have to calculate phi. For the solution, say the first plot is of force which is harmonic with an amplitude of f naught, and its profile is like this. Now the displacement is, for such a system, the solution will be particular solution of the type xp is a sine omega t minus phi. Omega is the frequency of the force, phi is the difference by phase difference by which the displacement is lagging. As is shown, displacement profile is this, its amplitude is a, this is a, we have to calculate. Its frequency is same as of the force, it is omega, and we have to calculate this phase difference phi. Now, first natural frequency relation we know is omega n is equal to under root of k by m. So omega n is, putting the value of k value is 20,000 newtons per meter and mass is given to be 200. So we will put it, we will solve it, we get that natural frequency of undamped system is 10 radians per second. So as is given in the problem, omega by omega n, omega is equal to omega n and frequency ratio omega by omega n is equal to 1 for the given problem. Now critical damping coefficient relation, we know it is Cc 2 times under root of Km. So when we solve, we put value of K 20,000 Newton per meter, mass of 200 kg, we get Cc value 4000 Newton second per meter. Now according to the definition of damping ratio zeta, C by Cc, so damping ratio zeta C by Cc, C is given to us, it is 200 Newton second per meter. We put it here. Cc we have calculated 4000. So damping ratio of the system comes out to be 0.05. It is a quite underdamped system. Now the relations for amplitude, we have derived A is equal to F naught amplitude of the harmonic force divided by stiffness whole divided by, now the denominator term is under root of this term 1 minus omega by omega n square, its whole square, where omega by omega n is the frequency ratio, plus 2 zeta omega by omega n its whole square. Now we put the values. Here we put the value of F naught, which is given to be 50 Newton. We put value of K. K value is Newton per meter. We put frequency ratio omega by omega n. It is 1 here and 1. We put zeta value to be 0.05. We solve that. The answer comes that system will vibrate with the magnitude of 0.025 m. Moreover, the phase difference relation tan phi is, we have derived, it is 2 zeta omega by omega n to 1 minus omega by omega n whole square. Now we put value of zeta, we put omega by omega n to be 1 in the numerator and denominator, tan phi becomes infinity. So we have a value of sine or tan phi infinity at phi of 90 degree. So displacement vector will be lagging the external force vector by an angle of 90 degree, and amplitude of vibration will be 0.025. Alternatively, we can solve the similar problem, this problem, with the help of a vector diagram. This is the vector diagram for the case where omega is equal to omega n, means the case of resonance as is the given. So in this vector diagram we observe that the phi phase difference is 90 degree. So we got the solution. And other thing which we get is amplitude of force vector is equal to c omega a. F naught is equal to c omega a, and amplitude of inertia vector m omega square a is equal to k. M omega square a is equal to k. So from this relation we get a is equal to F naught by c omega. Now for the present case, we get A is F naught by C omega, and omega is basically natural frequency, so F naught by C omega n. So we put the value of F naught here, which is given to be 50. Then we put the value of C, damping coefficient, we put the value omega n, which we have calculated 10, and we solve it. Again the amplitude value becomes 0.025 and the phase difference is phi 90 degree. So we have got the solution. by two methods. Now coming to the second problem, a reciprocating pump of mass 500 kg is driven through a belt by an electric motor of 3000 rpm. So what we get is mass is 500 kg, omega. Omega is angular frequency of external excitation in radians per second. Wherever we have been given the excitation frequency in revolutions per minute, means this we have been given the value n. Pump is mounted on isolators with the stiffness K value 5 meganewton per meter and damping coefficient is 10 kilonewton second per meter. Determine the vibratory amplitude of the pump at the running speed due to fundamental harmonic force of excitation of 5 kilonewton. So we have been given the amplitude of external excitation to be 5 kilonewton, and we have to determine amplitude of vibration of such a reciprocating pump at a frequency of 3000 rpm, and the solution plot is xp is a sine omega t minus 5. Now we have been given mass of 500 kg, stiffness 5 meganewton per meter, damping coefficient 10 kilonewton second per meter, n of external force 3000 rpm, and external excitation is f naught sine omega t, where f naught value is 5000 and omega we have to calculate from n. We know the relation omega angular frequency is 2 pi n by 60, where n is in rpm. So we get omega in radians per second. We put the value of n, which is 3000. We solve, omega comes out to be 314 radians per second. Now natural frequency of the spring mass system is under root of k by m. We put k value 5 meganewton per meter, mass of 500 kg, and omega n is 100 radians per second. Now frequency ratio omega by omega n we saw by dividing omega value is 314, omega n we have calculated 100, it becomes 3.14. So we have solved omega by omega n to be frequency ratio to be 3.14. Next is critical damping coefficient is 2 under root km. So 2 k value we put 5 mega Newton per meter, and mass we put 500 kg. We solve, it becomes 1 into 10 raised to power 5 Newton second per meter. Now damping ratio zeta is the ratio of damping coefficient to critical damping. We put value of C, we put value of critical damping. We solve that zeta for the system is 0.1. So in this slide, we have found the values of frequency ratio 3.14 and damping ratio 0.1, which we carry forward. So we have carried forward omega by omega n value 3.14, zeta value 0.1. Now we have to determine A, amplitude of vibration. Now making use of frequency response curve, which is a curve between amplitude ratio A by xs and frequency ratio omega by omega n. What we observe is Zeta is very small, 0.1, but omega by omega n value is 3.14. It means we are somewhere in this range, somewhere here. So this plot is an approximate plot, rather the values here are very less. So what we get is amplitude ratio will have very small value. We get an idea from frequency response curve for our problem. Now amplitude relation is f naught by k. In the denominator is under root of 1 minus omega by omega n frequency ratio square, and it's this term's whole square plus 2 zeta omega by omega n, this term's whole square. Now we put the values of f naught to be 5000 Newton, k value here. We put value of omega by omega n to be 3.14, and we put zeta value to be 0.1. So when we solve, we get that the system will vibrate with a very small amplitude of 0.11 mm, as is predictable from the frequency response plot. Next part of the problem is we have to also find out amplitude at resonance. Now we know frequency ratio at resonance is omega by omega n is 1, as we solved in the first problem from the vector diagram. So from the vector diagram, what we get is at the resonance, when omega is equal to omega n, the vector diagram is like this. Phi becomes 90 degree and external excitation amplitude is equal to c omega. We make use of this relation, equating f naught with the c omega a. We get a is f naught by c omega. Omega is equal to omega n. So f naught by c omega n. We put the values and we solve. This is the f naught value, which is given to be 5000 Newton. This is C, which is given for the R problem 10,000 Newton second per meter. We have calculated the natural frequency to be 100 radians per second. We put and we get that at resonance the system will vibrate at little higher amplitude of 5 mm. Now we will solve this method in an alternate way. We have derived a relation that magnification factor or amplitude ratio, which is ratio of amplitude to excess, which is zero frequency deflection or static deflection at resonance, when omega value is equal to omega n, it comes out to be 1 by 2 zeta. Now for the present problem zeta we have found, we put zeta value here, we put f naught excess is equal to now f naught by k. So we put value of f naught, we put value of k, we put value of zeta, again we solve, and the amplitude comes to be 5 mm. So we have found the amplitude at the running speed and at the resonance. We found amplitude at resonance with the help of a vector diagram, and also alternatively using the relation for magnification factor at the resonance. Thanks, my dear students. With this, the lecture is complete.